Well, we're talking about numerical integration techniques. In the last video, I talked about the trapezoidal rule, which was a pretty straightforward method of finding trapezoids, area under trapezoids, and taking the summation of them. But it is actually fairly simple, a simple process to find the area for a function under a parabola. And in a parabola, a good demonstration of this idea is that, well, let's just take the generalized area under a curve ax squared plus bx plus c, the capital A, B, and C are our constants, over some generalized interval from small case a to small case b, which represent fixed values. What would happen? Well, certainly finding an antiderivative of ax squared plus bx plus c is a simple matter. We get 1/3 ax cubed plus 1/2 bx squared plus cx, all evaluated on the interval from a to b, which gives us this expression, 1/3 a b cubed minus a cubed plus 1/2 b squared minus a squared plus c b minus a. Now, there's a lot of algebra in this in-between step that I'm skipping over. I'm sure everybody's disappointed and wants to see Professor Peoples' absolutely stunning uh, uh, algebra factorization skills at work. However, I'll just cut to the chase and say after I factored out b minus a over the common denominator of 6 from that expression, I was able to work it out that we took a squared plus b a times plus c. That should be a capital C right over here. Let me see if I can fix that up right here. Plus capital C plus 4 times a times the quantity b plus a over 2 squared plus b times the quantity b plus 2 over a, which is our sort of an intermediate value, right? B plus a over 2, that's the halfway point in our interval right there, isn't it? Plus c plus a b squared plus b subscript b plus a. Now, if we let p of x represent our polynomial, essentially what we're saying is that, all right, let's take our polynomial ax squared plus bx plus c. We will get a perfectly uh, um, serviceable area underneath that parabola every single time if we use the formula b minus a over 6 times the parabola evaluated at a plus 4 times the parabola evaluated b plus a over 2, right, the midpoint of that parabola, plus p of b, which is the other end point. It's interesting that it should put up that way, because if we think of it in that manner, well, what that really means to us is that we are dealing with a rule that tells us that we're just taking them 3 points at a time. In essence, if we had our curve here in pink of f of x, you imagine us taking the first point and 2 other points beside it, and we can use 3 points at a time for our evenly spaced intervals to give us an approximate area. Now, you can see that in this case it's not going to necessarily be a great interval, but we're using a curve to estimate the area under a curve, and if we had a lot more rectangles underneath this curve, we could actually do a reasonably good job of figuring out what that area would be. And so in this setup, we take 3 points at a time, and so it kind of works out like this. It's like we're saying take 1/3 of delta x, where delta x is b minus a over n. So b minus a over 3n times, when we work this through, we would find an expression that looks like f of x evaluated at the first point, a, that's f of x of 0 to us, plus 4 times f of x of 1, plus 2 times f of x of 2, plus 4 times f of x of 3, plus 2 times f of x of 4, and so on down the list until we get down to the last two, which would be 4f of x of n minus 1 plus f of x of n. And if you want to think about it this way, whenever we're dealing with our 3 points right here, if we have x of 0 and I have x of 1 right here and x of 2 right here, look at what happens when we get our heights as our y values right here. It's f of x of 0 plus 4 f of x of 1, right? We need 4 of these, plus f of x sub 2, but then we add that one twice because we're going now to the next curve where we take f of x sub 2 again, plus f of x sub 3, right? So that one's times 4. And right here, that's supposed to point down towards this little multiplier right here. And then, of course, x sub n right here at b. So you think about it, there's a couple of points that are that we need to know right here. First of all, this requires that we have an even number of divisions, right? So even number n, we must have an even number. This would not work with an odd number of divisions if we said 5 or 7 or something like that. The other thing is that the pattern that we follow goes 1, 4, 2, 4, 2, and the 4s and 2s repeat until we get to the very end at 1. So if it's an even division, of course, we do end up with 4 and then 1 as the last point right there at which we're going to estimate this. All right, example to follow.